All right, welcome back, everybody. This week we talked about Newton's laws in all of the other videos and in the things that you've read. So in this video, I'm just going to show you guys how to answer some of the questions, some of the practice questions, just some ways to work different types of problems, and just some important things to remember as we go along. So Newton's second law is the mathematical part of Newton's three laws. So it's going to be the piece that we use the most when we are discussing these different types of problems. Okay, it's the most important thing that we can add to our motion calculations. We can now take the force that's given, and if we know the mass of the object, we know the acceleration. If that acceleration is constant, we can use all the kinematic equations that we had last week and figure out how the object's going to move and other aspects of its motion. And so for a constant force like gravity or the braking force of a car, the acceleration is going to be constant, right? And so that's assuming that the mass doesn't change. So we're going to assume that there's no change in any kind of mass in any of these motions. Okay, but remember that Newton's second law is that the sum of all of the forces is equal to the mass times the acceleration. Okay, the net force is equal to the mass times the acceleration. I've left off a little mathematical piece here. I'm just trying not to complicate it too much. I included the kinematic equations again, just because we're going to use these, or at least a couple of these. Remember again that the direction, which way you go, matters. We need to pay attention to our signs as we're doing these problems. Make sure that you're kind of looking at how I do the signs and things in the examples and matching it up to what you're doing. And we're going to do a couple of different examples in this video for you to kind of get a feel of what you can do now that you know Newton's second law. In the first example, we have a 1,550 kilogram car traveling at 125 kilometers per hour. When it suddenly hits the brakes, the car applies a constant braking force of 4.56 kilonewtons. What's the acceleration once we apply the brakes to the car? Well, this is relatively easy to figure out. We just need the force and the mass, which we have. Okay, now one thing to be careful about, especially this week, are units, right? So 4.56 kilonewtons, that's the same thing as 4.56 times 10 to the third newtons, or just 4,560 newtons. We have a mass of 1,550 kilograms. To find the acceleration, well, let me do this real quick. If the force is equal to the mass times the acceleration, then to find the acceleration, we just need to divide by the mass. Another way of saying it is that the acceleration is equal to the force divided by the mass. Or in this case, 4,560 newtons divided by 1,550 kilograms, which will give you an acceleration of 2.942 meters per second squared. Now, this is a braking force. The car is traveling in one direction. The brakes are going to make it travel in the opposite direction. If we choose the direction that it's traveling to be positive, okay, then the braking force is negative because force is a vector, mass is not a vector, and so the total acceleration will be negative. If the object is slowing down, the acceleration should be negative. If it's speeding up, the acceleration should be positive. So what else can we learn about the car as it's slowing down? How long does it take for the car to come to a stop? Here's another important thing that I want to point out. Units are very important We know that the car is traveling at 125 kilometers per hour. That's given to us in the problem. I'm going to write that up here, 125 kilometers per hour. But we can't use kilometers or hours if we're going to use newtons. We need to convert things to meters and seconds. I'm going to show you guys how to do a unit conversion. And the next problem, I'm going to show you just the faster way to do it. Either way is fine with me. If you have any trouble with these types of conversions, please let me know and I can share some extra videos with you. What you want to do here to convert this to meters per second is you want to eliminate the units, or basically switch out the units. Right? So if we have hours here in the denominator, we're going to put that up here in the numerator. And there are 3,600 seconds in 1 hour. Similarly, we want to change kilometers to meters. So we're going to put that down here on the bottom. There are 1,000 meters in 1 kilometer. Now, just like in algebra, these things will cancel out. And we're left with units of meters and seconds, or meters per second. And so to calculate this, we would just multiply 125 times 1,000 and then divide by 3,600. This would just give you this, essentially. Which is equal to 34.72 meters per second. So this is the initial velocity that we want to use. Our final velocity, since it's coming to a stop, is going to be 0. If we want to figure out the time, then how long does it take? Then we can just use one of our kinematic equations. Now that we have the acceleration from the previous problem, minus 2.942 meters per second squared. We want to change the units. And so using one of our kinematic equations, final velocity is equal to the initial velocity plus a times delta t, or the change in time. So this is what we're looking for. The final velocity is 0. The initial velocity, 34.72 meters per second. A is negative 2.942. And then delta t is just the time that we're looking for. If you do a little algebra here, subtract 34.72 from both sides, and then divide. Change back. If we then just divide to get delta t, you should find that the time, when you divide these two, the time that it takes for the car to stop should be 11.80 seconds. And so now we know how long it takes for the car to stop. There's going to be one more piece that we're interested in, which is how far does the car travel in that amount of time? And so now we know a lot of things about the motion of the car. We know the acceleration from the first part of the problem, from the braking force of the car. We know its initial velocity from when we converted 125 kilometers per hour to 34.72 meters per second. We know its final velocity is 0. It's going to stop. And we know that it takes 11.80 or 11.8 seconds for it to stop. If we want to know how far it travels, well, that's delta x. That's the only thing we haven't found yet. And so using those equations, the kinematic equations, plus 1/2 a delta t squared. We're just going to plug all these values in and solve. 34.72. Be careful with your signs when you're solving these types of problems. The acceleration is negative, 2.942. It's slowing down the car squared. And this 11, this time in the second half is squared. This will give 409.696. You guys may get some slightly different answers due to rounding, but it should be within a decimal place or so. And the distance that it travels when you add these two up, 204.88 meters. So it travels about 200 meters before the car comes to a stop. So this is the simplest type of problem, motion problem, when you know the force or the braking force of a car. There's other things that we can do when we know some of the things that we've learned about Newton's laws. Okay, so when we have an object that accelerates very quickly, right, we can use the acceleration due to gravity as units of acceleration. You hear about this when you talk about jet planes taking off, right? G forces, right? Also on roller coasters, you experience G forces as you make those sharp turns. So we can use that as a unit. But to do that, first we need to figure out what the acceleration is going to be, right? So the mass, here we have an 11,500 kilogram airplane launched by a catapult from an aircraft carrier, is accelerated from 0 to 210 kilometers per hour in 3.2 seconds. We want to know how many G's does the pilot experience. First thing that we have to do is we have to convert 210 kilometers per hour to meters per second before we can do anything else, right? And this is our final velocity. It's accelerating to that velocity. So 210 kilometers per hour. Now, the conversion is exactly the same. We're going to do the exact same thing every time as we did in the last problem. We're going to multiply, we're going to divide by 3,600 to get rid of the hours. And then we're going to multiply by 1,000 to convert it to meters. And so we don't have to do the same thing every time, right? We can very easily just convert this all at once. Bear with me while I, we can convert this all at once by just multiplying by a single value. That's just 1,000 divided by 3,600. Or if we multiply this by 0.277, and it kind of goes on forever here, so 0.2778. What you should find is the final velocity here in meters per second, 58.338 meters per second. And so if you're converting from kilometers per hour to meters per second, you can always just multiply by this number. And that will convert it to meters per second. Now, to figure out the acceleration of the airplane, right? Acceleration is just the change in velocity, the final velocity minus the initial velocity, divided by time. Okay, this is a kinematic equation if we rearrange it, but this is also just the definition of acceleration. The final velocity from what we just calculated is 58.338 meters per second. The initial is 0. It starts from 0. It does all of this in 3.20 seconds. And so the acceleration, 18.231 meters per second squared. To find how many G forces that is, right, or how many G's that is, all we've got to do is divide by the acceleration due to gravity. And so to find the ratio, to find out how many G forces we have, we're going to take our acceleration we just calculated and divide by the acceleration due to gravity. So 18.231 meters per second squared divided by 9.8 meters per second squared. And we get 1.86 Gs. And so the pilot's going to experience 1.86 times the acceleration due to gravity on Earth. For the next question, I want to just remind you that remember the difference between mass and weight. Weight is a measure of your gravitational force on whatever Earth or whatever planet that you're on. Right? It's the gravitational force that you experience when you're standing on Earth. Right? Your weight will change if you are on another planet. You can see this rather clearly if you go watch folks from the 60s and 70s walking on the moon. So let's talk about the difference between weight and mass, right? Your mass is a measure of how much stuff you're made out of. That doesn't change no matter where you are. And so we can use the mass of an object to calculate its weight on any planet. So if we know that an astronaut on Earth has a weight of 2,250 newtons. Okay, your weight is a measure of the gravitational force you experience. I'm going to use a W for weight. Okay, your force is equal to the mass times the acceleration, or your mass, right, and the acceleration due to gravity. And so to find the mass of an object, we're just going to use the weight and divide by the acceleration due to gravity. So 2250 newtons divided by 9.8 meters per second squared. And this will give us 229.59 kilograms. Now that we know the mass of this astronaut, that mass won't change no matter where the astronaut goes. So we can now calculate the astronaut's weight on the moon. And so we're just going to call it the weight of the moon on the moon. It's going to be the mass times G, but we're still talking about the moon here. The mass of the astronaut was 229.59 kilograms. The acceleration due to gravity on the moon, which is about 1/6 the size of Earth, is 1.63 meters per second squared. And so the astronaut would weigh 374.23 newtons. That's a decimal point. On the moon. Very much less than the 2200 or 2250 that he weighed on the Earth. We can add another planet into this, and this is just to show you the difference between the Earth, the moon, and Mars. The acceleration due to gravity on Mars is 3.85 meters per second squared. It's somewhere in between the size of the moon, and the size of the Earth. So if we want to calculate the weight of the astronaut on Mars, 229.59 kilograms times 3.85 meters per second squared. And the weight on Mars is 883.92 newtons. So a little less than half of Earth in terms of weight. There are a few more things that we can learn about motions of objects, and we could really dive deeply into this, but I don't want to complicate the math much further than we already kind of are. I think you guys can do this stuff relatively easily, but we could make this complicated, of course, by immediately kicking a soccer ball at an angle. Okay, so if you're reading questions like this, think about things moving in straight lines, and it might be a lot easier to think about. We're not doing things in two-dimensional motion right now, though we did talk about that a little bit last week. Now we have a 492-gram soccer ball is at rest, and it's kicked with a force of 578 newtons, and it flies off at 15.4 meters per second. How long was the toe of the person kicking the ball in contact with the ball? So if we know the force that's applied, and we know how fast the ball is traveling, we can figure out how long the object was accelerated. First, we need to use Newton's law to find the acceleration. Okay, this is relatively straightforward, but there's one thing I do want to point out. The mass, 492 grams. Okay, there's 1,000 grams in 1 kilogram. You want to convert this to kilograms always. Always kilograms, meters, and seconds if you're going to use Newton's. Now to find the acceleration, well, the force, thanks to Newton's second law, the force is equal to the mass times the acceleration. The force is 578 newtons. The mass is 0.492 kilograms. And so the acceleration we can find by dividing by 0.492. And this will give us an acceleration of, and I kind of just flip the equation around, 1,174, sorry, turning pages, 1,174.80 meters per second squared. Seems like a large acceleration compared to what we've been talking about. But that's okay. You're kicking something, it's going from 0 to fast pretty quick. So it can have a pretty big acceleration. What would be strange is if it had this large of an acceleration for a really long time. And so let's see how we could find the time from this, right? So now we have the acceleration. If we want to find the time, well, we know it started at rest, so it starts at 0. It leaves after the force is applied at 15.4 meters per second. We know the acceleration due to the kick, right, due to the force, is going to be equal to 1,174.80 meters per second squared. This is from what we just found. If we want to find time, now we can just use that first kinematic equation. Final velocity is equal to the initial velocity plus a times delta t. Here the initial velocity is 0, so we can just get rid of this. The final velocity of 15.4 meters per second is equal to the acceleration 1,174.80, okay, and then times the time. So to find time, we just divide. Again, you guys, it's just a little bit of algebra stuff. If you're unfamiliar with the algebra, please reach out to me, and I will send you some videos that will help from other classes I have taught. If we calculate the time, 15.4 divided by 1,174.80, we're going to find that the contact time with the ball, 0.13 seconds. So break these things down into pieces, right? Remember that the gravitational acceleration only applies if something's falling, right? Or if you're talking about the weight of an object. Otherwise, find the acceleration using the force. Now, one more, it's a bit more of a complicated example, but I do want to discuss it. I did include a problem like it in your practice problems this week, okay? But that's why we're going to discuss it. A parachutist whose total mass is 78 kilograms is falling at 46 meters per second when her parachute opens, and then her speed drops to 10 meters per second in 4.25 seconds. What's the total force that her harness has to withstand? Okay, so we have a person here, okay, and they are attached to a parachute. When that parachute opens, okay, the person's falling 46 meters per second, right, moving downward. When that parachute opens, it's going to slow down, so the acceleration is going to cause it to decelerate. Okay, but when it slows down, the parachute not only has to hold the person from falling, it has to pull the person up so that it can slow down. Okay, and so the weight of the person, okay, and the tension essentially in the parachute are going to be in the same direction. So all we need to know is how much acceleration does the parachute apply. Okay, and so to do this, we have the initial velocity, okay, and the final velocity of the parachute, 10 meters per second, or I'm sorry, to find the acceleration, final velocity minus the initial velocity divided by time. We know the time as well. She stops or slows down to 10 meters per second from 46 meters per second in 4.25 seconds. So that's negative 36 over 4.25, which should give you negative 8.471 meters per second squared. So not only does the parachute have to pull back on the person enough to accelerate her at negative 8.471 meters per second squared, right, to slow her down that much. The parachute also has to account for gravity, right? If all the parachute did was hold her up from the gravitational force, right, then she wouldn't accelerate and she wouldn't slow down. She would travel at 46 meters per second the whole way. So the parachute has to do better than that. It has to pull back more than that. To find the total force her harness had to withstand, we have to add the acceleration due to gravity. And so the net force is equal to the mass times the acceleration. Okay, well, our two forces here is going to be the mass of, the mass is the same, okay, times the acceleration plus gravity. Or we could write, I'm sorry, this is 78 times 8.471. There's a few different ways to do this. Let me, I'm going to show you a different thing in just a second. Because we're adding these two vectors up in the same direction, right? The acceleration from the parachute and gravity, right? We can just add those two and say that the force is equal to her mass 78, I'm sorry. It's equal to her mass times the total acceleration, A plus G. Okay. A plus G, 8.471 plus 9.8 give you 18.271. And so this is 78 times 18.271. And you're going to get the same answer for both of these, regardless of how you calculate them. And it should be 1,425.138 newtons. 1,425.138 newtons. Same calculation, two different ways to think about it. Now, the last piece of this is to figure out how many times her body weight is that. And so how many times her weight is the force that she experienced? Well, she experiences a force of 1,425.138 newtons. Her weight, right? So we're essentially looking for a ratio of the force she experiences to her weight. Her weight is going to be mass times just g, right? mg, mass times the acceleration due to gravity, which is 78 times 9.8. That's an 8. And so that's 1425.138 divided by 764.4. And these will both be in newtons because we're just finding a ratio. How many times her weight is the force, right? And you would find that it's 1.86 times. Think about what the question's asking you as you're working through these problems. Try not to let them get you confused. If you have questions, email me, ask, watch over how I did some of these problems. Everything that I did here should help you in solving everything that you have in your practice problems that are mathematical. But if you have any questions, please feel free to reach out to me this week. And next week, you guys will talk about the universal law of gravitation and gravity. And we'll do a few more problems with those as well. If you have any questions this week, please let me know.